Welcome to the last part of our NumPy solution. So in the last videos we have found optimal solutions for our n-best equals 1 strategy. So that means that the best prince in the test group is our reference prince. And in this video we will variate the n-best parameter to find the optimal combinations of both parameters. So the n-best parameter and the test group size parameter. And maybe we find even better strategies. We are actually working with two different target metrics. So we have our very picky princes who want to maximize the probability of getting Prince Charming, and we have our more risk-averse princess that wants to maximize the expected or the average quality of her selection. And let's go here to our picky princess. So for our picky princess, we have learned that the best strategy is to have an optimal test group size of 36.8% of total applicants and to choose the best prince in the test group as reference prince. And I think already our intuition says that we cannot further optimize here our strategy by increasing the n-best parameter. However, we still want to analyze the impact of increasing the n-best parameter. So instead of having only one curve here for the n-best equals 1 strategy, we now want to produce many curves or many graphs. So for example, for the n-best equals 2 strategy, n-best equals 3, 4, 5, 6, 10, 25, 90 and so on. Alright, so therefore now let's start coding. And we want to have a graph or a curve for all n-best strategies for n-best equals 1, 2, 3, 5, 10, 25, 50, 75 and 90. And therefore we are using here a nested for loop. So first of all we are iterating over all n-best strategies, and then for each n-best strategy we calculate the probability of getting Prince Charming for each possible test group size. So for example, if we have n-best equals 1, then we calculated the probability of getting Prince Charming for all test group sizes from 1 till 100. And if we have n-best equals 50, then we call our function here for all test group sizes from 50 till 100. And we are using 10,000 simulations. And we are actually storing the results in the list results. So we should get here a nested results list. So let's do this here. First of all, we have to define here our n-best list. And we should actually have 9 lists in our results list. So we have here a nested list. So let's first of all check this one here. It's still calculating. Alright, so now let's check the length of our list. It's 9, and let's also check our results list. So here the first list is actually for our strategy n-best equals 1. And here we are starting with the results of the n-best equals 2 strategy and so on. So let's also plot here our graphs. So we have 9 graphs, and actually we are iterating over all n-best strategies, and for each n-best strategy we are actually plotting the graph here. And actually we are using here an interactive graph, so let's do this. So here we can see the blue curve or the blue graph is for our n-best equals 1 strategy. And it's no surprise that the n-best equals 1 strategy is the optimal strategy. So in combination with an optimal test group size of approximately 37% gives us the maximum probability of getting Prince Charming of 37% here. And the more we increase here the n-best parameter, the less likely it is to get Prince Charming here. Alright, so now let's head to our more risk-averse princess. So first of all here let's exit our interactive graph. And our more risk-averse princess want to maximize the average quality or the expected quality. So let's go back here. So this is the graph where we have here on the y-axis the average quality depending on the test group size for our strategy nbest equals 1. And we already know from the Python standard library solution that we can further optimize and actually maximize here the average quality by increasing the nbest parameter. And that's exactly what we want to do now. We want to calculate and plot here the graph not only for the nbest equals 1 but also for many nbest strategies, so for nbest equals 2, 5, 10, 50 and so on. And we want to find the total maximum here. So let's do this. And again here we are defining our nbest strategy, so we have nbest equals 1, 2, 3, 5, 10, 25, 50, 75 and 90. And again here we are using a nested for loop, so this is nothing new. And instead of calculating the probability of getting Prince Charming, we are calculating the average. And again we are using 10,000 simulations and we are storing the results in the results list, so let's do this here. Alright, we are finished and now we can plot our graphs. And we can see here the blue curve is the nbest equals 1 strategy, then the green curve is the nbest equals 2 strategy, and the red curve here is the nbest equals 3 strategy, and so on. And it's obviously very hard to see here the total maximum, so we can also zoom here in. And we can see here that the blue curve, the red curve, the purple curve and the yellow curve are quite close together. So the maximums here are quite close together. And actually we want to be more precise. We want to find here the total maximum, and therefore it might be a good idea to further increase the simulations, but actually limit here our combinations of the test group size and the nbest parameter. So the optimal nbest parameter should be somewhere between 2 and 10. And the optimal test group size should be somewhere here between 15 and 70. So let's define here our nbest parameters from 2 till 10. And also we define here our possible test group sizes from 15 to 70. And now again we want to calculate for each possible combination here the average quality. And therefore in a first step we have to produce our combinations. So we create here an empty list combinations, comps. And for every nbest strategy here in our nbest NumPy array, we want to combine with the possible test group sizes. So let's simply run the cell here and let's have a look then at our combinations. So let's have a look here. So we have actually here a nested list with many rows and 2 columns. And the first column here shows us the nbest strategy, and the second column here shows us the test group size strategy. So we are starting here with nbest equals 2 and the test group size of 15, then we have 16, 17 and so on until 69. So we have here all possible test group sizes until the very last excluding. So here we have from 15 to 70, and then the very last test group size that we consider is then 69. And then we have here the nbest equals 3 strategies. And let's go to the end. So here we have the nbest equals 10 strategies, starting with a test group size of 15 until 69. And let's also determine the amount of combinations here, so actually the number of rows in our NumPy array. So we have 495 combinations that we want to check. And for each combination we want to call our princess NumPy function, and we want to calculate the average quality. And the test group size is actually here the second column, and the nbest parameter we get here from our first column of our NumPy array. And then we are actually storing all results in the results list. So let's do this. And we are using here 25,000 simulations. So we have 495 combinations and 25,000 simulations. So this could take a while here. Alright, we are finished now, and let's check here the length of our results array. So we have 495 combinations, and for each combination we calculated the average. And what we want to do now actually, so here we have a NumPy array with our combinations. So we have our first column where we have the nbest parameter, then we have the second column where we have the test group size parameter. And now we want to add our results list as actually our third column here. And we can do this with the method np.hstack. And first of all, we are transforming our combinations list. So combinations is here not a NumPy array, a two-dimensional, but still a nested list here. Sorry for that. So we are creating a NumPy array out of our combinations list. And also for our results lists, we are transforming it into a NumPy array. And we have to reshape here our results NumPy array to have 495 rows and one column. So then we can horizontally stack our NumPy array comps and our NumPy array results, and we assign the variable nbest size average. And let's also have a look here. So we can see here that we have a two-dimensional NumPy array with 495 rows and 3 columns. So for example here we have the strategy nbest equals 2 with the test group size of 15, and there we get the average or expected quality of 92.45. And now we can make a scatter plot here. So let's simply do this, and then I can... Alright, we do not get here a graph, and it might be the case that we didn't close here our last interactive graph. So this is actually the pitfall of interactive notebooks. So we have to first close here our graph. So we never can produce two interactive graphs at the same time. And now we can try it again here. And actually what you can see here is some kind of a three-dimensional graph. So here on the x-axis we have the size of the test group. Then here on the y-axis we have our nbest parameter. So for example here we have the combination nbest parameter equals 2 and size of test group equals 30. And then actually each scatter or each dot here in our graph has a color. So let's also check what we coded here. So we produced a scatter plot, and on the x-axis here we have actually the column at index position 1. Here it's the test group size. And on the y-axis we have our nbest parameter, here our column at index position 0. So we're actually producing here a two-dimensional scatter plot. However, each point in our scatter plot has a characteristic color. So we defined here color, and the color of each point actually depends on our third column here. So on the average quality of the princes. And here with the CMap parameter, we can define a color map. So there are many color maps, and here we define the magma color map. So we have here colors from black to yellow. And with Vmin and Vmax, we can actually define the scale of our color map. So 0 should be black and 100 should be yellow here. So if one strategy returns an average of 0, then the point here should be black. And if one strategy returns here the average of 100, then the point here should be yellow. So actually here in our graph we are searching for the most yellow point, and it's actually very hard to see it here. And therefore we can change the scale here of our analysis. So but before we are doing this, we want to determine the maximum in our average column here. So the maximum average quality. So let's do this here. And the maximum average quality that we can expect is 94. And we can also determine the row here of our NumPy array, where we find the maximum here. And we can do this with the argmax method. So here we can see that the row 130 gives us the maximum average. And we can also slice for the row with the maximum average by slicing here our n-best size average NumPy array and selecting here the row at index position 130. And we want to do this for all columns. So let's do this. So here we get actually our best strategy. So we have n-best equals 4. We have a test group size of 35. And by doing so, we get an average or expected quality of 94. Alright, so now let's go back to our graphical solution. And we want to further scale here our color. So we set the Vmax to 94.2. So let's do this here. And Vmin to, for example, 80. And here we can see that our optimal solutions are actually concentrating in this area here. And we can further scale our color. So let's change here from 80 to 90. And now we are getting here even closer. And let's further increase here Vmin to, let's say, 93.2. So now we can actually more or less locate our optimum here in this area. So maybe we can further optimize this. So now we can see here that we have only one dot, which is actually really yellow, and we can further here zoom into our graph. So let's do this. So actually here we have only one dot, which is yellow. So this dot is yellow, and we have our maximum at 94.2. And we find the maximum here with a test group size of 35 here and with the n-best strategy of 4. So in order to maximize the expected or average quality, we have to split our total applicants into a test group with the size 35. And then we are selecting the fourth best prints in our test group as the reference prints. And then in the select group, we are selecting the very first prints that has higher quality than the reference prints. Alright. And now last but not least, let's also create a histogram for our optimal strategy. So we are calling our prints as NumPy function. We set the size test group to 35. We have n-best equals 4, and we are using 100,000 simulations. And our function should return the results array. So let's do this here. And then we want to plot here our results array as a histogram. We use 101 bins, so let's do this. Again, here we have to first close here the interactive graph. Alright. So here we have the histogram for our optimal strategy if we want to maximize the average quality. So we have 100,000 simulations, and we can see here that only in, let's say, 1,300 cases we get no prints at all. And in total it's very, very likely to get a print that has higher quality than 80. So we can also further zoom here in. And here we have the bin for Prince Charming. So we have 11,000 times Prince Charming. And then even more frequent, we have the Princess quality 99. And we have the highest frequency for the Prince with quality 98. And it's actually more or less unlikely that we get a prince below the quality 80 or 85. And we can also count the number of occurrences that we get no prints at all. So this is here actually the risk. And the risk of getting no prints at all is only 1.3%. And we can also calculate percentiles here for our results array. So we want to have the percentile 2.5 and 97.5. So in 95% of all cases, we get here a prince between quality 84 and 100. And there's only a risk of 2.5% that we get a prince with lower quality than 84. Alright, so now this was our analysis with 100 applicants. And now the interesting question is, if we scale here our applicants, so if we have 1000 applicants, can we then simply say that our optimal strategy is here a test group size of 350, so 10 times 35, and nbest equals 40, so 10 times 4. So if you like, you can find out on your own and make your own code here. And we are actually now finished here with the solution. And in the next video, we will make a short summary of our results. And we will also define more complex strategies, which you can also then simulate on your own. So thanks for watching here the videos, and I hope you have fun here with further simulating and calculating here our Princess Challenge. Thanks again, and see you in the next and last video. Bye.